about means. We're going to move on from proportions. We're going to talk about means. And remember that means, when we found confidence intervals, they also use t-tables, right? So we're going to use those t-tables here as well. So in order to use your data, you have to make inferences about a population beyond your sample. The first thing is you must have a representative sample. Of the population for the question of interest. If you're trying to predict election results, you cannot just ask millennials about what they want to do. Or just baby boomers, right? I mean, that would be a non-representative sample. Hypotheses and conclusions apply to the larger population. That's represented by the sample. And one thing that you should think about, if the distribution is highly skewed, you should consider analyzing the median instead of the mean. And that's something called a non-parametric method, and we don't do those in this class. So, all right. So we're going to talk about significance and hypothesis tests with just one mean, or all we're going to do this is a general introduction, then we're going to do one mean today. So with one population mean, that symbol for that is mu, remember that? Mean would be mu, proportion would be p. And for example, we might want to test if the mean body temperature really is 98.6 degrees Fahrenheit or something else, right? That's one potential thing. We might also ask about paired data. What was the symbol for that? Mu sub d. D bar is the sample stuff. Mu sub d. For example, we might ask if the mean difference in height between college men and their fathers is 0. And difference in means of two populations. Mu1 minus mu2. We may ask if the mean time watching TV per week is the same for men and women. Oh no. This is too bad. So one reason we call these tests significance tests is because the conclusion about whether to reject the null hypothesis is based on a sample statistic being like significantly far away from where we think it should be, if that null hypothesis were true. So here, these are the same 5 basic steps as in the last chapter. So first step is figure out your null and alternative hypotheses. And in this case, the null hypothesis might be that a specific number, like the average body temperature, is equal to this specific thing. In this case, we have to use t-statistics, but the t-statistic is more or less the same as the z-statistic. It's whatever you get for your sample statistic minus your null value over the null standard error so sample stat minus null over standard error of null. And in the case of like a single mean, our null value is some mu value, which I'll call mu naught. What's the sample statistic you get in this case? What's the thing you use to estimate mu? X bar. And remember that the standard error of X bar was sigma over root S over root n. First, S was sample standard deviation. So this will be, once again, S over root n. That doesn't change from last time.
Is to be the standard error of mu?
It is, and to estimate that, you would need to know sigma for real, and so you have to use S to estimate it.
Okay.
Whereas the proportion standard error formula actually uses the P naught thing. So this one is a little bit different. And the only thing other than after this, it's all the same except for you use that T table instead of the Z table. That's the only difference, okay? And we'll talk about how to do that in examples. It'll make more sense when you actually look at some numbers, okay? All right. explain whether each of the following statements is true. This is kind of a review of hypothesis testing. So do you ever accept the null hypothesis? No. Never. You just fail to reject it. Okay, Noontide. Is the statement reject the null hypothesis and accept the alternative, are those the same?
Yes.
Yes. When you reject H naught, it's in favor of HA. Okay, we're going to review this one more time because I don't know why you guys seem to know it, but it was on my notes and so it's still here. So is this parameter of interest one population mean of paired differences, or the difference between two different means? So nutrition trends have changed over the years, and this may affect growth. Researchers want to know whether the mean height of 25-year-old women is the same as the mean height of 45-year-old women. So is this two different groups or pairs? Two different groups. How could you have made it pairs?
When they were 25 and then again when they were 40.
Mother and daughter.
Oh, yeah.
Does that make sense? So this would be a mu1 minus mu2 situation. And the null hypothesis might be to assume that those two things are equal to each other, right? How about, I don't like this question, but we'll attempt to anyway. You're going from New York to Chicago. You have a choice of flights. You can find out how many minutes late each flight was for a random sample of 25 days. So there probably are lots of flights between these two cities, right? And maybe flights at a specific time of day are later than others. Does that make sense? So does it make sense that you would kind of pair all the flights that are at the same time together?
Yeah.
Okay, so this is an example of paired data. All flights for a specific time. May be paired together. But I don't like this question so much, so don't worry about it being on the test or anything. But one would suspect that maybe that flights that happen later in the day because they have to have more things sort of, the planes have to get to various places, right? And if you mess up at this time, you might mess up later times, right? So I'd suspect that planes that fly away later in the day are the ones that are more messed up. Does that make sense? I have a friend who works for Alaska Airlines. I'll ask her what she thinks, because she does this data for them. Okay, let's actually test the hypothesis because it'll make a lot more sense once we've done one. So what is the average body temperature for real? And a paper published in JAMA presented evidence that the normal body temperature is actually less than the conventional 98.6 degrees. So what would the null and alternative hypotheses be in this situation?
The null hypothesis is
It is equal to 98.6. And HA, their evidence was that it is less than this value, right?
Yeah.
So that would be that mu is less than 98.6. Degrees Fahrenheit, yep. Obviously not Celsius, because that would be like impossible.
we can reject them.
Right away. Yep. Okay, let's find the T statistic. So they have a sample of 16 adults, and the sample value was 98.2 as the sample average, and the standard deviation was 0.497. So this is X bar equals 98.2. Does that make sense? What is this thing? Is that the standard error or standard deviation? Standard deviation, so that's the S. Okay. And our T value is X bar minus mu over S over root n. Okay, so x bar is 98.2. What's mu?
98.6.
And the S over root n is 0.497 divided by,
16, which is 4.
oh, I put in 30 in my notes. Root of 16, which is 4.
Age 30.
Age, I made the same mistake on my notes. That's gonna be annoying. Okay, so tell me what you guys get for this.
I got negative 3.212, or 3.22.
3.22? Okay. Let's get that? Okay, great. 3.22? Okay. Is everyone okay with how to find the t statistic? Okay, now let's talk about how to use that table. So with t statistics, we have degrees of freedom, which is equal to n minus 1, which in this case is 15. Yep. Okay. Okay. Now, do you see how you have, what we've used in the past for t-values was the front page of this sheet, right? We're going to use the back page now. So you have degrees of freedom and then the absolute value of the t statistic. So a p-value in the table is the area, so at the top it says a p-value in the table is the area to the right of t. So this actually does the opposite of what z-tests do. So if I were to say plug in t equals 3.22, it would tell me the area on the right of it all of a sudden. So the probability that t is less than or equal to negative 3.22, and, oh, yes, is the probability that t is bigger than or equal to positive 3.22. This is still symmetric. And then go in your, is everyone okay with that change? Yeah? Okay. Now, do you see how, if you look at degrees of freedom equals 15, you go over and the t-values are the things at the top of the columns. Is the t-value of 3.22 listed?
No.
Was the biggest t-value you're given? 3. What p-value comes out of that? 0.004. What happens as you go across that column to the p-values?
It's bigger.
I think the p-values get smaller.
Oh, you moved your pen the opposite direction.
Yeah, as you go across from left to right, the
Left to
p-values
right,
get smaller, right? So this is less than 0.004. Does that make sense?
Yeah.
And the reason this is so hard is because you have to have values for all these different degrees of freedom. It's hard to give every single possible t-value. Does that make sense? So when you're given a table, you just have to tell me if it's less than or what it's less than, okay? Here's how you can verify this in Excel. So in Excel, you do equals t-dist for t distribution, and the arguments are t, degrees of freedom, and then the last one is tails. Not like heads, tails. It's 1 or 2 tails, exactly. So for our case, what would go in for the t value? Let's think. I think we should do 3.22. I don't know what it will do if you do negatives. I tested with the 3.22. Degrees of freedom was 15, and then tails is it a one-tailed or two-tailed hypothesis test? This would be 1. And that comes out to be 0.0028. Does that jive with what we said?
Yes.
Yeah. Okay. Alrighty. So like I said, I think before, on your homework, let's have you find these things exactly, just to verify that what you have in the table is right, okay? use alpha equals 0.05 to determine whether or not you can reject the null hypothesis. So can you reject the null hypothesis? Yeah, your p-value was equal to 0.0028, which is less than 0.05. So you reject H naught in favor of HA. Okay, make a conclusion. So you conclude, or we conclude, what about average body temperature? Average body temperature is less. Does the table that you have, this table 8.3, tell you what to do if the test is two-sided?
Double.
It says double the value? Okay. All right. So let's just practice using that table to find some values. So we have H naught is mu is equal to some mu naught, and HA is mu is not equal to mu naught. We have n equals 81 and t equals 2.0. So first of all, is it two-sided or one-sided? Not equal to would be two-sided. And what are the degrees of freedom? 80. Okay, so look at your table, go to 80, and then I think that 2 is actually on there, isn't it?
Yes.
So what p-value does that give? So we'd have a p-value of 2 times 0.024, or,
0.048.
yep, exactly. Okay. Yeah. If alpha was 0.05, you would reject H naught, right?
Right, we doubled that because it's a two-sided.
Exactly, yep. That was what you were gonna ask?
Yeah.
Okay. This one is that, you see that HA has a specific direction?
Yeah. This one-sided.
That's one-sided. I think I have a bit of a typo here. I think this is supposed to say t equals positive 2.0. Because if your mean is going to be bigger than your null value, you should get a positive t statistic. First was if it was less than, you would get a negative t statistic. We had that happen in the question where we were talking about is the proportion of men who write lists lower than women. That was a negative z value. Same kind of principle applies here. But the kicker here is this is one-sided. What would your p-value be? 0.024. Good thing I only have one page left. Okay.
This is the end of chapter 13?
No, we'll do more next week.
Oh.
I just kind of got a little bit ahead. So suppose a study is done to test the null hypothesis, H naught, where mu is equal to 100, and a random sample of 50 observations results in x bar equals 102 and s is equal to 15. Can you find the standard error? What's the formula for standard error in this case? It would be s over root n. Okay, what goes in for s?
15.
Over root.
No, 50.
Yep. So that comes out to be,
15 over 7.07.
yeah, so I got 2.12. You must get that? Yep. Okay, great. Once you've got that, can you find the t statistic? So t is x bar minus mu over the standard error of x bar. So that's x bar was 102 minus 100 over,
2.12.
0.0 or 0.943. That's what I got. Okay. Part C. On the basis of the information that you're given, can you find the p-value for this t statistic you got? In particular,
The alpha?
yeah, well, you need, the alpha would tell you to reject or not reject H naught, but you know the null hypothesis.
Do you know if it's two or one-sided?
You don't know if it's two or one-sided. See, well, that's not actually clear. Does that make sense? Why not?
Yeah.
They didn't specify what HA was, right? So without HA, you can't tell if this is one-sided or two-sided. And for one-sided, let's just figure out what the p-value is. P would equal, so look for the, which one is, what is it closest to?
It's the closest we have. So
The closest we have, we had 50 people, so degrees of freedom, we 49, so I got, it's closer to 1 point, so 0.1, P is bigger than
Yeah, very good.
0.103. If you do it in Excel, like I did, you get P is equal to 0.175. But do you see why P is bigger than 0.103? Because the T would be even more left of 1.28, so, and if it was two-sided, would this let you reject H naught? No. So, and two-sided is going to get even worse, isn't it? Because it's going to double the p-value, so rejected nothing. Okay, one last one. I think we can finish this. So a university is concerned that it is taking students too long to complete their requirements and graduate. Does it sound like UAF? Yes. And the average time for all students is 4.7 years, which doesn't sound so bad to me. The dean of the campus honors program claims that students who participate in that program in their first year have a lower mean time for graduation. Can we call that a self-selected sample? There is no way to pull the records of all the students who participated in that program. And a random sample of 30 students is taken, and the mean and standard deviation completion time for these students is 4.5 years and 0.5 years. So they want to figure out is this 4.5 a lot better than that 4.7? So first step is to find H naught and HA. So H naught is that there's nothing going on. So that would be that the mean for people in the honors program is 4.7. So mean in honors, same as the rest.
First, I need to deal with that record-keeping system.
Yeah, I know, a pretty crapper. And then the alternative is that the honors program has a lower average, right?
Yeah.
So that mu is less than 4.7. Honors program is lower. Okay, step 2 is to find your T statistic. So that's T is X bar minus mu over the standard error of X bar. So in your sample, what did you find? How long did the sample people take to complete their degree? 4.5 versus the overall average, which was, and then the standard error is, over square root of 30. points for the denominator, that's right. And I got negative 2.19 for kind of everything. Okay, step 3 is to get the p-value. What's our degrees of freedom going to be? 29. Okay, that table that you have, oh, it has that. Look at that. Huh. So the probability that t is less than or equal to negative 2.19. Same as t bigger than or equal to positive 2.19. So is 2.19 given in your table as a t statistic, though? But it's in between 2.0 and 2.33, right? So look at 29. What corresponds to 2. What's the p-value corresponding to 2.0?
2027.
So do you agree that this is going to be less than 0.027? But bigger than what? 0.13? If you figure this out in Excel exactly, you get p equals 0.018. So what does this p-value lead you to do? Reject H naught. Accept HA. In words for this context, students in the honors program, or students who participate in the honors program, do finish faster. If I say that's a self-selected sample, do you know what I mean? That people, there might just be better students in the honors program to begin with, right?
Right.
So it's not like that program is doing the helping, it might just be the students are different. So just to be clear,